Okay. Hello, my name's Rod Selfridge. I'm here at Queen Mary on the Media and Arts Technology PhD program, and I'm in my second year. I'm supervised by Josh, Andrew, and Andy. And my topic is, well, real-time synthesis of aeroacoustic sounds, which includes the weather, and you'll hear some sort of wind sounds earlier on, later on. But it's really trying to look into the physics behind the models and how we can construct these to generate the sound effects. So, first question really is, what is an aeroacoustic sound? The best way of sort of describing it to people when I've spoken to them is if you imagine the sound of a sword going through the air or wind blowing past a fence, the whistling sound that you hear. There's obviously weapons. One of the things that have been sort of one of the main research areas is bomb bay doors and landing gear in planes. And if you think about sort of what's going on there, when a landing gear sort of opens up and it comes down, you're creating something that the wind is air sort of hitting against, but you're also creating a cavity, which will create another type of sound. And some of the main sound objects that I'm looking at during the presentation, well, during my PhD, is the aeolian tone, the cavity, and the edge tone. Most of the work I've done is on the aeolian tone, and that's what I'll probably speak most about during this talk today. Now, coming off the bottom of my slide for some reason. Let's see if I can get that back. No. That's better. So, why physical models? Well, there's signal-based models out there that generally do a very good job of creating a sound effect. Computationally simple, and one of the things, though, that I sometimes struggle with is the parameterization of them, sometimes not quite matching the physics that's going on in the background. So, for an example, changing the frequency to a higher frequency to represent speed, but it doesn't quite capture all the relevant nuances of the physics that's underlying the process, which is generating the sounds. We've got physically inspired, so we've added some knowledge of the physics or some sort of simplification to try and create a better sound, or then full sort of physical models, which is what I'm looking at, of designing and achieving accurate sounds based on fundamental equations. But I'm trying to also create real-world parameters, which is sort of much easier to understand, like speed, dimensions, distance, these type of things. Now, for aeroacoustic sounds and sort of anything that involves the air, computational fluid dynamics, that approach, entirely accurate solutions, really, but a seriously high computational cost and generally not in real time. So the models that I've been looking at are based in pure data, trying to generate it all, and it's all in real time. So where do you start? Well, I came in, I had very little experience in pure data. I have no knowledge of what fluid dynamics is whatsoever. You speak to your supervisors, you find out what drinks they like when you're down in the pub, and you try and gauge your area, try and learn what you've got to do. You look at Andy's book out of the library and you learn a bit more. But being at Queen Mary, you're kind of lucky as there's lots of experts kicking about. So one of the first things I did was I went to a reader in aeroacoustics, knocked on his door and sat down, and I've basically asked his advice. What's the physics going on? What is aeroacoustics? And we chat for a while, and he tells me sort of the story of Navier-Stokes equations, and he shows me these, and he sits down and he's basically this quote saying, "Turbulence is the work of the devil." It looks chaotic, but it's not. It's very mathematically planned. It's just extremely complex. And he talks about how we can solve them and how they're normally solved by solving the Navier-Stokes equations, which, again, are really complicated. And he sort of says if Boeing was going to do this to try and find out the sound as their wing was going through or their landing gear was opening, they would spend months letting the computations run, and then they would get their answer. And he says to me, what's the processing time? And I want it to be real time. 5 seconds? No, I want it to be real time. I want the sounds generated as audio rate, basically. So he sat and he talked and he thought, and he decided looking at monopoles, dipoles, quadrupoles, so compact acoustic sources. Monopole, if you think of like a football and it's just pumping out like this. A dipole is going side to side and that has a radiation pattern like this. And a quadrupole, I can't quite demonstrate with my hands, but that's one of the other sources that go up. So I start with the aeolian tone, and this is sort of where the major research I've been working on so far. You see a wee sort of diagram there of what's happening. Now the air is flowing from this direction, and as it flows, it creates vortexes, and they're shed from either side. So as they go flying off each side, there's two different forces that are happening there. There's a drag force causing it to pulse forward and backwards. And then there's also a lift force, if you think like an aircraft wing, they've shed vortexes. Because it's cylindrical, it goes side to side. So there's a lift force going side to side and a drag force back and forth. And the drag force pulsation's twice the lift because it's always in the same direction. So we're starting to say, okay, I can replicate these sounds based on the dipole sources. And this is where I start looking at formula. What do I need to know? I need to know the frequencies that are generated. So a lot of the time I'm looking back in history, because to solve these without solving Navier-Stokes and to do it in real time, you can't really look at computational fluid dynamics. You're going to look further back, and back in history or back in the sort of 70s, 60s, they did tons of work before all this processing power was available to solve the Navier-Stokes on finding semi-empirical equations that will predict the sound that's produced. Back in 1878, there was a Czech physicist called Vincent Struel who defined this formula. And what he did was he was putting his cylinder on an arm and he was spinning it round. He knew what speed it was traveling at, and he knew the diameter, and he could measure the frequency. And he found this relationship, and he thought it was a constant of 0.2. And he used this, and he was pretty much accurately predicting frequency of what the sound would be generated as it moved through the air. Turns out it's not exactly 0.2. It varies, and it varies with something called the Reynolds number. The Reynolds number is basically a rating on how turbulent the air is around the object that's creating the sound. So you can start at laminar and you can go right up to the areas called critical. I don't understand all the areas, but I did find another equation basically in a book by paper by Fay in 1998, which gave this relationship between the Reynolds number and the Struel number. And then the two constants are basically set for each different shedding sort of turbulent area. So I can get the constants they've given me in this paper, and they've got the Struel number. It'll get the Struel number if I can get the Reynolds number. Thankfully, the Reynolds number is not too complicated to calculate. Basically, you get the air density, the air viscosity, the diameter of the object, and the speed of things going on. You get the Reynolds number. Have the Reynolds number, plug it back into the equation Fay had, I get the Struel number, plug it back into Struel's, I get the frequency of what's going on. So that's a big chunk of what's the sound that we're trying to reproduce. Next is the gain and the propagation directions. So searching away, speaking to Dr. Avital and others, and I found this a book actually by Goldstein in 1976, who gives an equation for the acoustic intensity. The equation probably reaches off the edge here. I've simplified it to this because this is probably one of the most important things when dealing with a sound effect. And that's basically that the acoustic intensity is proportional to the wind speed or the airspeed to the power of 6. So you double your wind speed and the intensity goes way, way up. And I'll speak about that later, of how that becomes an issue. You've got also things like the elevation angle in there, speed of sound is in the equation, the distance between you. And this is a sort of two-dimensional propagation pattern of quite high speed. It's about 0.2 Mach, which is about 69 meters per second of the air flowing this way. The cylinder is in the center there, actually bends back the radiation pattern. So we've got the radiation, the gain, the fundamental frequency, but it's not just a straight sine wave of this is the frequency. It's got a bandwidth and it's got harmonics. So again, I'm looking into the bandwidths, and there was a paper by Norberg in 1987, and he actually printed the data of the relationship between fundamental frequency and the bandwidth compared to the Reynolds number. So the more turbulent it gets, the wider the bandwidth of it is, the more laminar or sort of clean the flow is, the narrower it is. So this is basically, if I found the best fit equations, and it's a Q value for a bandwidth filter. It's directly proportional. So that's how I generated the sound in pure data. I have the bandwidth filter with the Q value varying with the Reynolds number. The fundamental frequency would be the center frequency number. And hey presto, I've got the fundamental tone sound. Now there's also harmonics. In a paper by Harden in 1984, he stated that there was basically harmonics at, what's the third harmonic, because of the fundamentals at 0.2, the third, and then the fifth. The drag force is at the one at 0.4 because it's double the lift, and it has one at 0.8. Whether the one at 0.8 is particularly heard is debatable. So I have all the data that I can create now one Aeolian tone compact source model. So two different plots here. This one is my model. This one is a fluid dynamic software package called Fluent. The wind speed is 42.67 meters per second, and the diameter of the cylinder is 0.0127 meters. Okay, it's two-dimensional, azimuth is 0, the elevation is 90, and a distance of about 12 meters. But in fairness, the gain is not really as relevant as the frequencies. So we can see a problem here in my model. Now, the reason I have seen plots that are very similar and do have these harmonics far more visible on this one, and the reason I believe that it's probably inaccurate now is because the Reynolds number is so high that the harmonics gain value comes right down. The one, I haven't found the, well, couldn't see the exact Reynolds number in the Harden paper when he states these, but I believe it's far lower than what the Reynolds number is in this particular physical case. The Reynolds number is about 33,000. You do see, this is where it is on this model here, and we actually have a peak here, which is the drag, which is not visible on mine. The roll-off is 1 over f squared, which is on mine pretty similar, and obviously you got the build-up, but the frequency here pretty much bang on is what I was looking for. So there's further physics and further questions about the amplitude of harmonics and how to add them into my model. But overall, that is produced in real time. This took 2 days in Fluent. Probably a more skilled practitioner could probably get it down to less, but that's the main difference of what we're trying to do. I'm trying to make the real-time model as accurate as possible based on the physics, and obviously there's questions to be asked, but we've got it's pretty much spot on harmonic frequency of where we want it to be. So the parameters that are available are airspeed, the diameter, the length, the distance, the elevation, and the azimuth. So it's basic physics. It's not anything that's too complicated like spectral centroid or something along those lines. It's real sort of hands-on parameters, which a sound designer of any level I would think would understand, but they can also, game engines can also set these parameters for you. So this is what I did in Unity. This is the first thing I ever did in Unity. I'm not a Unity programmer or anything, but here you'll hear the sound of the wires, the horizontal wires, as you approach them. I use Andy's wind model, generating the sort of the wind speed, although it's hacked by me, so I can set an average meters per second. So I'll just let you have a listen and see if it comes out. Let's play that again. So things like the azimuth and the elevation and the distance was all just taken from Unity, thrown via OSC into pure data and the sounds generated. A few other sounds just for you to listen to. All 12 cylindrical objects at varying diameters, various lengths, various distances. So those first two, the 32 meters per second, that's roughly a hurricane speed. 24 meters per second is obviously a bit lower, and I've put sort of quite a few small objects very similar close to each other to try and represent a fence. This next one, it's 64 meters per second. If you remember, the acoustic intensity is speed to the power of 6, so I had to decrease the gain. But this is basically twice the speed of a hurricane. So again, one of the advantages is that if you're needing something that would represent twice the speed of a hurricane, well, it's difficult to try and find. It's 140 miles per hour winds, but in a physical model, you can basically put the number in and get the answer out or the sounds out from the physical dimensions that you have. So what else can I do with this alien tone? Maybe this is slightly away from weather synthesis. But I decided to try putting them all on a line and seeing what I could get. So I battered out this sound model. So there I've put the compact sources in a line, and I obviously just move them with the sword. I've put the camera as your viewer, so that's in your listening position, and all the distances, elevation, azimuth is all based on the different where the sources are placed on the sword, and that's what creates the sound. Another limitation I found when doing this is a direct one-to-one mapping was in the next animation, this night character moves about Mach 2 across the screen. Your physical model doesn't handle that. Well, my physical model doesn't handle that because the sound just goes boom through the air. So there's another sort of little research question there. But so what I did was I put 8 different compact sources in a row. The majority of them at the tip, and then spaced back down and a couple more further down. The reason that they're tip, because the tip moves much faster, and that's where the majority of your sound is generated. I created a pure data model, and this sort of give you the ability to vary the length and the thickness and listener speed on all the angles. And so an example of a thin sort of Zorro type sword. And then you can make it thicker and a bit shorter for this next one. And when I first got this working, my wife shouted upstairs to me saying it sounds like a little dog. but that's sort of, so what I did was I connected up to a Wii controller, and you can move the Wii controller and try and get these sounds, and I can set this up for the end if anybody wants to have a sort of muck about with that. I then got to thinking, what else can I do? I've got swords. What other things can it represent? So I looked up the dimensions of a baseball bat and what a sort of major league player can swing, what sort of speed they can swing it at. I put all the physics of that into the model. So it's you can clearly hear a slightly different sound, or a bigger dog, as my wife would say. And I thought, well, that's actually, I was quite happy with that. And then I thought, right, another thing I can do. So the next one I did was a golf club. And I was testing these sounds out in my hometown of Carnoustie, which is only famous for golf, and London. And the people back home got it straight away, and the people in London didn't get it at all. But I'll let you hear that just now. So what I did was I got a real crappy bit of additive synthesis and added it into the next one. And I suppose it's sort of the psychological part of the sound design where people can make much more of a connection to the sound. So I made it like this. Then everybody kind of, all right, I understand what you're doing. They got it. So the next thing I did with the sword sounds was a wee listening test to see how people rate it for authenticity. It's 3 samples, 2 different other synthesis methods, and my models. So clearly the Adobe and SoundSnap, which are both samples, they came out top. Sony, it's not a great sample in fairness, for so it didn't do so well. The lowest one is sound synthesis method by a guy called Niles Botcher. And I spoke to him, and he's like, well, we didn't make our model for accuracy. It's all for just enjoyment and perception and how you get the feel of it. The Bashi was done by computational fluid dynamics. They spent a few hours offline getting sound textures and creating the sword sounds in that way. And then my models 1 and 2 are the sort of thinner and the thicker sword sounds that you heard. So they did sort of as similar to the Sony and the Bashi, and maybe a little bit better than Botcher. But what I also did to sort of just to test how much physics was people appreciated was I knocked some out. I suppose one of the way of looking at it is if you're building a building block to do a sculpture, and you put all the physics in, and then some of it just might not be relevant, and you knock it out. So that's what I did here, and it did very well. So I set the Reynolds number at 0.2 rather than worrying about its relationship to the Reynolds number. I set the bandwidth on the bandpass filter to a set number, and people seem to rate it better than the one that had the full physics in it. Not necessarily means that the full physics is wrong. It just means for this model and this swords that maybe people prefer that. So what's the next thing I can do with it? Is this something I probably shouldn't do, because the physics involved here is not the same as the alien tone, but I couldn't help myself. I was like, I want to make a propeller model. I got a diagram online of what a propeller model dimensions, and I made each source basically a cylinder representing the exact proportions that are here and the angles. I find out what's sort of perpendicular to the wind. And I created the propeller model with 2 propellers on it, played it away, and I thought this sounds not too bad. But it's very rare that you'd hear a propeller without an engine, so I stole Andy's 4-stroke engine. I linked the 2 up with the speed, changing the RPM of the propeller. On this, you can really hear the difference between, or as the speed goes up, the audio to the wind speed to the power of 6, and the acoustic intensity really changes. So in this clip, you can hear the motor's really, really low level, but it steps up and you really can hear the propeller coming through. So that has got a work in progress because when the propeller moves around, it's actually hitting into turbulent air, and that's what's one of the big sound generating principles, rather than just a cylinder going through. Sort of with the sword model, you're not hitting any turbulence, so it's there's more work to be done there, but it's a reasonable start. One of the other major factors in aeolian tones and when wind's hitting wires and cables is natural frequencies. So the natural frequency, it's relative to the tension and the length and the mass density. But basically, if you recall, I was talking about the vortexes shedding. Well, when they match the natural frequency, the gain is greatly increased. And what also happens is the wind speed might go up a bit, but the mechanical process says, no, you're still going to shed at my speed. So it creates a kind of lock-in, and it's so the tones actually stay at set tones. It's not as relevant at higher modes in sort of the lower sort of 1st, 3rd harmonics, 8th harmonics. By the time I get to the 80th harmonic, it's much more damped effect. But this is an aeolian harp in Japan. It's quite low speed, and you'll hear the sounds. You'll hear the sounds of the sea, but what you'll also hear is the tones are very set frequencies, which is again something that I want to build within my model. So as you heard the sort of set frequencies there and how they didn't really move. Interestingly enough, when I talked to Christian about this, he was like, oh, I had exactly the same type of synthesis problem, and we kind of collaborated and hopefully taught me a bit of how to achieve this on my model. Cavity and edge tones are sort of another area of further development for me. I won't talk about them for much at all, but for the cavity especially, something called the Rossiter's formula, which calculates which frequencies are present based on the sort of dimensions of the cavity that's there. It's again a dipole source, and it sort of radiates back. The flows coming this way, and it radiates the sound back in this direction. It's got a 35-degree there. I've seen another one that says 45. So research into this and how to get the gains and obviously the propagations and the bandwidth, stuff like that. That's again another area. So we can look at buildings, we can look at doorways, things like that, which the wind's blowing against. Swords, some swords have grooves in them. These are present when you swing it as well, so we can get more different types of sort of cross sections. The edge tones, sort of similar thing, but obviously no resonant cavity on them. So I'm at the end. It's a model based on fluid dynamic principles. It's semi-empirical equations, which give you the result which, say, computational fluid dynamics won't do in real time, which was the whole point of trying to generate them. The parameters are things like speed, distance, length. They're quite practical, and hopefully most folk can understand and be able to use them. And in the perception, they were pretty much as good as other synthesis models, sometimes higher. And obviously, when you heard the sword, the propeller, the baseball bat, the golf club, the wires, it was all one model. It was just used in different ways. So we've created a Zorro sound. And if you want to push the boundary even further, you can always change the atmosphere and still get practical sounds. Thank you very much. I'll pass over to Chris now.